Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by SWAYAM. In the previous session, we learned about basic logic gates, logic diagrams and truth tables. Realization of Boolean expression using AND, OR and NOT gates were also illustrated. This session deals with two more important logic gates, NAND gate and NOR gate. You may recall De Morgan's theorem from Boolean algebra. For any two variables a and b, a plus b complement is equal to a complement dot b complement and a dot b complement is equal to a complement plus b complement. This will be helpful for you for easy and better understanding of NAND and NOR gates. So, we start with NAND gate. The word NAND can be expanded as NOT AND. A NAND gate produces the inverted output of an AND gate, that is AND function with a complemented output. The logical expression for NAND gate is written as a dot b complement. The logic diagram of NAND gate is shown here. It has two inputs, say a and b, and an output, say x. The bubble in the logic diagram symbolizes the negation. A NAND operation can also be realized using AND and NOT gates as shown here. Two inputs, a and b, passed through an AND gate and the result is a dot b. This is inverted using NOT gate. And finally, we get the same function a dot b complement. The function of this NOT gate is represented by a bubble in the NAND logical diagram. We also can have an n input NAND gate. If we consider the inputs as a, b, c up to n, the corresponding output will be x is equal to a dot, b dot, c dot, etc. up to n, the whole complement. Now, let us write the truth table. A NAND gate produces a high output when any of the input is low. That is, if any of the input to the NAND gate is 0, output will be 1. If both inputs of the NAND gates are 1, then the output will be 0. So, the truth table for NAND gate will be like this. For a and b, 0, 0, the result is 1. For 0, 1, the result is 1, 1, 0, it is 1, and for a is 1 and b is 1, the result is 0. Here, when both a and b are 0, or if any of the inputs a and b is 0, the output is 1. If both inputs of NAND gate is 1, the output will be 0. According to De Morgan's theorem, a dot b whole complement can be expressed as a complement plus b complement. This can be verified from the truth table given here. A is 0, b is 0, then a dot b whole complement equal to 1, a complement plus b complement is 1. And this is how for all the combinations we have written. The last two columns of this truth table indicates that NAND operation is equivalent to OR with inverted outputs. When two inverted inputs, say a complement and b complement, pass through an OR gate, it produces the NAND function. That means a complement plus b complement is nothing but a dot b whole complement. In this aspect, the NAND function is also negative OR. Due to this property, a NAND gate is used to detect one or more lows or zeros in a circuit. Now, let us see what are the applications of NAND gate. A NAND gate has a universal property, that is, it can be used to implement other logic gates, NOT gate, AND gate, OR gate, NOR gate, etc. We will be discussing about the universal property of NAND gate later in this session. Being a universal gate, NAND gate can be used to implement any logic circuits. Since a NAND gate can be used to detect low signals at the input, It can be used in applications such as check lower level of fuel or water or chemicals in containers, etc. All advantages and uses of other logic gates can be listed here, as all logic gates can be implemented using NAND gates. The next is NOR gate. The word NOR implies not OR. The NOR gate produces the inverted output of an OR gate. That is, NOR function is nothing but OR function with a complemented output. The logical operation of NOR gate is defined as x equal to a plus b whole complement. This is the logic diagram of NOR gate, a bubbled OR gate with two inputs, say A, B, and the output x. We can draw the NOT OR equivalent diagram of NOR as shown here. The two inputs A and B pass through an OR gate and the output A plus B is complemented using NOT gate to obtain A plus B whole complement. And let us write the truth table. The truth table for NOR logic operation is AB00 x is 1, AB01 x is 0, and for 1 0 0 and 1 1 it is 0. From the truth table we infer that a NOR gate produces a high output when all of its inputs are low, and it produces a low output when at least one of the input is high. In other words, we will get an output 1 for a NOR gate if all the inputs are 0, and we get an output 0 if any of the input is 1. NOR also has a different representation, that is negative AND, because according to De Morgan's theorem, A plus B whole complement is equal to A complement dot B complement. This can be verified from this truth table 0 0 1 1, then 0 1, A plus B whole complement is 0, A complement dot B complement is 0, and it goes like that. We see that both expressions give the same output. Thus, we can say that a NOR gate is equivalent to AND of inverted inputs. And in this aspect, this can be specified as negative AND. Because of the above property, a NOR gate is used to detect all lows or zeros at its input. More about applications of NOR gate. The first one, a NOR gate has a universal property. That is, it can be used to implement other logic gates, NOT gate, AND gate, OR gate, NAND gate, etc. The second point, since a NOR gate can be used to implement any other logic gates, it can be used to realize any Boolean function and hence any logic circuits. And the next point, since a NOR gate can be used to detect all low signals at the input, it can be used in monitoring applications such as aircrafts functioning, etc. And the last, all applications of other logic gates is applicable to NOR gates, as all logic gates can be implemented using NOR gates. Now, let us explore the universal property of these gates. What is meant by the word universal? It means a property which is applicable to all cases. What are universal gates? Universal gates are those which alone can be used to implement any logic gates or logic circuits. Using them, we can construct any Boolean expression. The universal gates we mentioned here are NAND and NOR gates. Let's see how can they be used to implement other basic gates. First, let's consider the universal properties of NAND gate. Here we are going to implement the basic logic gates NOT, AND and OR using only NAND gate. Let's start with a NOT gate. A NOT gate using NAND gate is implemented by connecting all of the inputs of NAND gate together. Consider the case of a 2-input NAND gate. If inputs are connected together, we will be giving only a single value, either 0 or 1, to both of the input lines of the NAND gate. When A equal to 0, output will be 1 by the function of a NAND. And when A equal to 1, then both inputs to NAND gate will be 1 and the output will be 0. That is, when we input A equal to 0, the output is 1. And when A is equal to 1, the output is 0. The input is complemented and it is nothing but NOT operation. It is the logic diagram for NOT implemented by NAND gate. For a better understanding, you can use this truth table. A equal to 0, then A dot A whole complement is equal to 1. So, we get A complement is equal to 1. Then A equal to 1, here A dot A whole complement equal to 0 and C A complement also equal to 0. Next, we implement AND gate using NAND gate. We use two NAND gates to implement an AND gate. The output of a single NAND gate with two inputs, say A and B, is A dot B whole complement. If we complement this result, we get A dot B, the output of AND gate. Just now we have seen how to complement using NAND gate. So, just combine these two NAND gates as shown in the diagram. The first NAND gate produces A dot B complement and the next NAND gate complements the result. Thus, we obtain A dot B. The truth table assures the result. See, A is 0, B is 0. A dot B complement is equal to 1 and A dot B whole complement that is A dot B is equal to 0. The next 0 1, A dot B complement is 1. For A dot B complement the result is 0 and it goes like that. This is how a logical AND operation is implemented using NAND gates. Now, we move on to implementation of OR gate using NAND gate. We know the output of a NAND gate is A dot B whole complement that is equal to A complement plus B complement. To obtain the function of OR gate, that is A plus B, we need to complement this. So, the logic we use here is A complement dot B complement whole complement that is equal to A plus B. This can be implemented by using three NAND gates as shown in the logic diagram. The first AND gate, where its input is A, produces A complement. The second AND gate, where its input is B, produces B complement. These inputs A complement and B complement are fed to the third NAND gate to produce A complement dot B complement whole complement, which is equal to A plus B. The logic is clearly shown in the truth table, where the first two columns are the inputs A, B. Next is A complement, B complement, then A complement dot B complement whole complement. And see the results for 0, 0, 1, 1, 0. Next 0, 1, we get 1, 0, 1 and for the final value 1, 1, 0, 0, 1. Next, we implement NOR gate using NAND gate. We implemented OR gate using three NAND gates and we got the output A plus B. If we apply another NAND gate to invert that result, we will get A plus B whole complement. That is logical NOR operation. The logic diagram for the same is shown here. We can verify the result using the truth table given here. See the columns A, B, A complement, B complement, then A plus B whole complement. We get the results as for 0, 0, A 1, 1, 0 and 1. For the next, then for 0, 1, the values are 1, 0, 1, 0 and the last row you can see that for A is 1, B is 1, A complement is 0, B complement is 0 and the next two columns are 1 and 0. This verifies the result. It is also possible to implement XOR and XNOR gates using NAND gates using the above techniques, as they are combinations of OR, NOT and AND gates. Now let us see the combinational logic using NAND gate. We have already discussed that a NAND gate can act as NAND or negative OR based on De Morgan's theorem. This property is utilized in implementing logic expression using NAND gate. Let's see how a Boolean expression can be implemented using a NAND gate. Consider the expression x is equal to PQ plus RS. This can be implemented using NAND gates as shown here. The inputs of first NAND gates are P and Q and results in PQ whole complement. The inputs of second NAND gate are R and S and it results in RS whole complement. The third NAND gate produces the result PQ plus RS. Next, let us discuss on the universal property of NOR gate. NOR gate is another universal gate by which we can implement other logic gates and logic circuits. First, let us see how can we implement NOT gate using NOR gate. A NOT gate is implemented by connecting all the inputs together as in the case of a NAND gate. Consider the case of a 2-input NOR gate. Give the same value to both input lines of the NOR gate as shown in the diagram. Either give both input as 0 or give 1. When the input A is 0, the output will be 1. And when A is equal to 1, then both inputs to NOR gate will be 1 and the output will be 0. Hence, we get the inverted output, that is the NOT function. Looking to the truth table, you can read the logic of implementing NOT by NOR. When A is 0, A plus A whole complement is 1 and A complement is 1. When A is 1, the second column gives you a 0 value, or complement is also 0. Next, implementing AND gate using NOR gate. We know the output of a NOR gate is A plus B whole complement, that is equal to A complement dot B complement. So, A dot B, that is the AND function, can be obtained by A complement plus B complement whole complement. Let's implement this logic using NOR gates. The first NOR gate receives the input A and produces A complement. The second NOR gate in the diagram receives the input B and produces B complement. And to obtain A complement plus B complement whole complement, we use one more NOR gate with inputs as A complement and B complement. This gives the final result A dot B. The truth table for this logic diagram is given here. For the values AB 0 0, the results are 1 1 0. When A and B are 0 1, it is 1 0 and the final value is 0. Then 1 0, it is 0 1 0. And when A and B are 1, the final result is 1. This truth table for this logic diagram clearly shows how NOR gates can be used to implement the logical AND operation. Coming to the next implementation of OR gate using NOR gate. Here we are using two NOR gates to implement the OR gate. It is similar to the AND implementation of NAND. When using one NOR gate with two inputs A and B, we get the output A plus B whole complement. We use one more NAND gate to invert the result and finally we get A plus B, the OR function. The truth table is shown here, which can be used for better understanding. The values of AB 0 0, final result is 0. Then for A is 0 and B is 1, the result is 0. A is 1 and B is 0, the result is 0. And when A is 1 and B is 1, complements are 0 0 and the result is 1. Next, NAND gate using NOR gate. NAND means not AND. This is the requirement. We have already implemented AND gate using 3 NOR gates. What do we need next? Just complement this result by using an inverter or NOT gate. This is done using a single NOR gate, and we will get A dot B whole complement. The logic diagram can be drawn like this. You can verify the result from the truth table. For the values A, B, 0, 0, the result is 1. A dot B complement is 1. Then for 0, 1, it is 1, 1, 0, 1 and 1, 1, the result is 0. Now, you might have understood how to implement NOR equivalent of different basic logic gates. The next, we create circuit for a logic expression using only NOR gates. We know that NOR gate can also act as negative AND based on De Morgan's theorem. This property helps us in implementing other logic circuits using NOR gates. Consider the Boolean expression x is equal to p plus q dot r plus s. The logic diagram for this expression using only NOR gates, which is shown here. The inputs of first NOR gate are p and q, that results in p plus q complement. The inputs of second NOR gate are r and s, which results in r plus s whole complement. The third NAND gate produces the result p plus q whole complement plus r plus s whole complement, the whole complement, which is equal to p plus q double complement dot r plus s double complement, which in turn equal to p plus q dot r plus s, which is the desired result. Similarly, we can construct the basic XOR and XNOR gates using NOR gates, as they are the combinations of AND, OR and NOT gates. Both NAND gates and NOR gates play a vital role while designing functional parts of a computer and can be used to implement functional units of alarms, monitoring systems and many other electronic devices. We have one more method to implement logic circuits using NAND or NOR. We use these steps for the same. The first step, build the logic diagram with AND and OR gates. You can use both complemented and uncomplemented literals as input. And the second step, redraw the diagram using NAND or NOR equivalents. Then in the third step, remove all pairs of cascaded inverters, and in the next step, remove inverters connected to single external inputs and complement the corresponding literal. What is left will be the NAND or NOR equivalent logic circuit for the given expression. To illustrate, let us consider the function a dot b complement plus c dot a plus b dot d. Implement this using NAND. This can be implemented using AND and OR as shown here. First, draw the diagram using AND and OR. Then substitute each gate with its NAND equivalent. Then we get the next diagram. There are few gates with single input which are not numbered. Observe each of them, and if there is a pair of inverters, that can be removed. Otherwise, complement its input literal by removing the gate. This gives you the final circuit. The same approach can be used to build NOR equivalent circuits too. Let's summarize the topics we discussed in this session. The two important gates, NAND and NOR, were explained in detail in this session. Their properties and equivalent expressions were clearly illustrated. Also, we learned to build logical circuits using only NAND gates and only NOR gates. This gives you a fundamental knowledge to proceed with combinational circuits. With this, we come to an end of the session. Thank you for watching. See you in the next session. Bye.